Okay, so lecture 3.2, basic probability theory. The mathematical model for a class of measurements is called the probability space and is composed of a mathematical triple of a sample space, omega, a sigma-algebra, F, and probability measure, P, typically denoted as the triple omega F P, each of which we will consider in turn. The sample space, omega, of an experiment is the set representing all possible outcomes of the experiment. If a coin is flipped, the sample space is heads or tails, where H stands for heads, T stands for tails. If a coin is flipped twice, the sample space could be omega equals the set heads, 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 tails, tails, heads, tails, tails. Exactly. However, the same experiment can have different sample spaces. For instance, for two coin flips, we could also choose omega equals, the flips are the same, okay, cool. And the flips are different.
We have only two outcomes at the same time.
So it's the same experiment that was done here,
Yeah.
but we could define the sample space differently.
So if it is defined like that, we don't think about the order of it happened. The order of the event, like if one is head or one is tail, so first.
Right, in this second sample space, we would say that one of the possible outcomes is that the flips are the same.
Head and tail.
Yeah, and then so that would be this guy and this guy. And then the other outcome is that the outcomes are two different. So heads, tails, tails, heads. We base our choice of sample space on the problem at hand. An event is a subset of the sample space. That is, an event corresponds to a yes or no question about the experiment. For instance, event A, remember A is a subset of omega, in the coin flipping experiments, two flips might be heads, tails, tails, heads. That could be the event that we're describing. A is an event that corresponds to the question, is the second flip different than the first? A is the event for which the answer is yes. Okay, so it's an event. Because events are sets, we can perform the usual set operations with them. Do a little example here. Consider a toss of a single die. We choose the sample space to be 1, 2, 3, 4, 5, 6. Single six-sided die. Let the following define events. A is defined as the set. The result is even. So there are three possibilities there: 2, 4, or 6. B is the set. The result is greater than 2, and that happens when the result is 3, 4, 5, or 6. Find the following event combinations: the union, the intersection, the differences, and then the complement differences. So we have A union B which is equal to what?
2, 3, 4, 5, 6. All of them.
Yeah, so 2, 3, 4, 5, 6, right? We have A intersect B, which is equal to what?
4 and 6.
4 and 6. The ones that are in common. We have A minus B. 2. Yep. B minus A. It was 3 and 5. Yeah. And we have A complement minus B. So A complement is going to be the odd ones, right? 1, 3, 5. So we could do this in 2 steps. 1, 3, 5 minus B, which is the evens, right? 2. Is that right? No, result greater than 2. 3, 4, 5, 6. 3, 4, 5, 6. Just 1, right? Great. Okay. The sigma algebra F is the collection of events of interest. Often, F is the set of all possible events given a sample space omega, which is just the power set of omega. Remember, the power set is the set of all subsets of a set. Sets. When referring to an event, we often state that it is an element of the sigma algebra F. For instance, we might say an event A is an element of F. We're finally ready to assign probabilities to events. We define the probability measure as being a map from the sigma algebra F to the interval 0 to 1. It's a function satisfying the following conditions. For every event A in F, the probability measure of A is greater than or equal to 0. In other words, probability of A is greater than or equal to 0. 2, if an event is the entire sample space, its probability measure is unity. So we have the probability of the entire sample space happening is equal to 1. If events A1, A2, etc. are disjoint sets, which mean they have no elements in common, then the probability of the event occurring, which is the union of A1, A2, etc., is equal to the sum of the probability of each of these. Essentially, since they're disjoint, there's no overlapping that's happening. We conclude the basics by observing 4 facts that can be proven from the above definitions. So the probability of the empty set the probability measure is 0 for the empty set. The probability of A union B, so 2 events A and B, equals the probability of event A plus the probability of event B minus the probability of the intersection of A and B. Because otherwise you'd be double counting that intersection, right? 3. If B is a proper subset of A, then the probability of B is less than the probability of A. In fact, the probability of A minus B is equal to the probability of A minus the probability of B. So not only do we know that probability of B is less than the probability of A, we know by how much. Okay. We also know that the probability of event A1 union A2 union continued on is less than or equal to the probability of event A1, plus the probability of A2, etc. Okay, so those are some basics with probability theory. We aren't going to go down like 1,000 rabbit holes of probability. We're mostly going to be focused on getting us to measurement and doing probability density functions and doing statistics eventually. Okay, so that's what we're doing in probability theory, but this is the sort of the basic stuff, probability. All right. Questions? Okay.